as you said, this is a blockchain 101 session. My name is Basit Shafiq. I'm the chair and associate professor in the computer science department at Syed Babar Ali School of Science and Engineering at LUMS. So this blockchain, again, as you said, this is a disruptive technology, a new technology, although this was there for a long time, since 2009. But we all became aware of this, or most of us became aware of this in the last 5-6 years when we looked at Bitcoin, its rise and fall, and then again rising again. But this blockchain is not just simply a cryptocurrency. There are very interesting applications that have been developed or that can be developed using this blockchain platform. So my objective in this session is to give you a fundamental idea, cover the fundamentals of blockchain, and then discuss how this blockchain can be used to develop different applications. Also, we'll look at some of the existing applications of blockchain, including cryptocurrency. I'll use the example of Bitcoin, and then give you some example of smart contracts just to illustrate how smart contracts can be used to develop distributed applications. And then, if time permit, I will also give you another example of an application from e-government domain. Okay, so what is blockchain? Blockchain, again, the textbook definition of blockchain, if you go to Wikipedia or any internet source, they will say blockchain is a distributed ledger, or rather a decentralized ledger. Ledger, as all of us we know, is basically a book of accounts which records different transactions or all the transactions of that account. So blockchain is no different than a ledger. It records all the different transactions, and then the ledger keeps on adding. So all these transactions, they are stored in the ledger in blocks. So you have one block which includes a set of transactions, and then you have another block which links to the previous block with a different set of transactions, and so on. So you can consider each block in the blockchain as different pages in your ledger. Now, however, in a traditional or conventional ledger, there is one single party, one trusted entity that keeps that ledger. In blockchain, we don't have a central or trusted entity who is managing this ledger. In fact, this ledger is kept in a decentralized manner by a community of peers, or each one may have a complete copy of that ledger, which includes different transactions. And as you know, this ledger, you may add more transactions to the ledger. So these peers, they are also going to add more transactions in their block or in their copy of the ledger. So one interesting thing in distributed systems or in databases, I'm sure most of you are computer science student, so you have the idea about transactions in the context of databases. So when you add transactions to a database system, there is a central DBMS system that commits a transaction. So there's a single authority. If there are multiple transactions submitted, that DBMS manager, it records these transactions in order of their occurrence to maintain, to have a consistent state of the database system. Now here, all these transactions are added by different peers. So we need to have a consistent state of that ledger. So all these peers who are maintaining or managing that ledger need to agree on a shared consistent state of that ledger, and that is one very interesting protocol for ensuring consistency in a distributed systems, or in the context of a blockchain. And you must have heard proof of work, which is used by Bitcoin, Ethereum. So we are also going to discuss the fundamental of that proof of work, what it enables, and so on. So this is basically the agenda of this session. Now I'll begin by giving a description of what is a block in a blockchain. So if you look at a block includes multiple transactions, which you see over here. Now each transactions, all these transactions are stored in the body of the block, and then you have a block header. Now in the body, in addition to these different transactions, you also have hashes of each transaction, and all these hashes are combined together to compute the hash of all the transactions. So all these hashes are organized in a Merkle tree data structure. There is a reason Merkle tree data structure is used. The reason is if you want to verify a transaction is part of a given block or not, you have to compute the hash of all the transactions and then combine those. So if there are n transactions, you will have to compute n values. But if you organize these hashes in a Merkle tree, then you need log n hashes. You need to compute only log n hashes. So assuming we have computed the hash of all these transactions, so this here, the root hash, this is the hash of all the transactions which are stored in this block. Now each block refers to the hash value of the previous block. So this hash value that you see over here, this is the hash value of a previous block. So you also have a block, if this is block number n, this hash value, previous hash, is the hash value of block number n-1. And then you have this nonce, which is a random value. So the key challenge over here for any node who prepares or who write this block is to come up with a random value such that the hash value, the combined hash value of the hash of all these transactions, root hash plus the hash of previous block plus this nonce, satisfies some properties less than some target value, and I'm going to discuss that a bit later in this presentation. But before doing this, I would like to just discuss what type of hash value or what type of hash function is being used. It's not the simple hash function that we use in the hash data structure. This is a cryptographic hash function which generates the hash value through a very complex computational algorithm, and that computational algorithm must satisfy these three properties. One is collision free, meaning no two input hashes should map to the same output hash value. So you cannot have two distinct input values, say x1 and x2. They produce the same output value. They will always produce a different output value. Number two is pre-image resistance, which means that if you are given a output hash value, it is extremely difficult, or it's nearly impossible to guess a input value which you can give to a hash function, and that will generate the given output value. So you cannot guess any input value by looking at the output of the hash function. Finally, avalanche effect, which is if you make a very small change in your input, then the resulting hash value, the resulting output hash value, that the change in the output hash value will be huge. For example, if you look at these two input text here, they are very similar, except for the fact that in the first input hash value, T is in uppercase, and in the second input hash value, you see T which is in lowercase. Now, if you compare the output hash value of these two input, you will see they differ in almost every digit. For example, if you compare these digits one by one, almost all the digits are different. So this is what we mean by an avalanche effect. So you need to remember these three properties, and we'll come back to these three properties later when we'll discuss proof of work. Now, what does blockchain enable? We talked about decentralization, we talked about a distributed ledger, but why do we need a blockchain? So again, we can think of different applications where we require decentralization, persistency, auditability, and privacy to some extent, and blockchain enable all these. Decentralization here meaning that you do not need a trusted third party that will keep the ledger and validate all the transactions in the ledger. So you cannot trust a single party. Rather, there is a community of peers, and that community may have malicious peers, honest peers, but together they are managing and maintaining the ledger. However, there is one important assumption that we require, which is majority of these peers who are maintaining the ledger are honest. There could be malicious peers, but they are in minority. Persistency. This means that it is impossible or nearly impossible to delete, roll back, update, or modify any transaction once that transaction is included in the blockchain. So if a transaction is included in a blockchain, it's very unlikely or not possible to change any of that transaction which is part of the blockchain. Auditability. All the transactions which are in the blockchain can be easily verified and they can be tracked. Anyone can verify the transactions that have been committed to the blockchain. Finally, anonymity or privacy. Blockchain does not provide 100% anonymity or privacy. Rather, it provides pseudo anonymity. So each user interact with the blockchain using a address, which is typically the public key or the key given to the user. And the idea here is all the transactions will not, all the transactions made by a user will not have the username. Rather, it will have the user address or the key given to the user. So the anonymity or privacy is provided using that key. If that key cannot be linked to the real identity of the user, then blockchain is private. But if some background knowledge is available to a user, then that privacy or anonymity cannot be guaranteed. So in that sense, blockchain provides pseudo anonymity, not complete anonymity. Okay, now there are two types of blockchain, public blockchain and private blockchain. And again, these can be further categorized as permissionless blockchain or permission blockchain. So a public blockchain is a blockchain in which all the records are visible to everyone. Everyone can read all the transactions that are recorded in a public blockchain. However, only the public blockchain may differ whether anyone can write any transaction or update the ledger, or only authorized nodes can update the ledger. So if anyone can update the ledger. This is a public permissionless blockchain. An example of public permissionless blockchain is the Bitcoin blockchain or the Ethereum blockchain. A public blockchain can also be a permissioned blockchain where anyone can read the transactions recorded on the blockchain, but only authorized nodes who have the permission can update the ledger or can write to the blockchain. So that's a public permissioned blockchain. Now, if we look at a private blockchain, in a private blockchain, nodes can read or write based on their authorization. So in a private blockchain, the records are not publicly viewable. Only authorized nodes can read the transactions on the blockchain, or they can write based on their authorization. So that's the difference between public and private blockchain. And again, further categorization of these blockchains as permissionless blockchain or permissioned blockchain. So Hyperledger, you must have heard about Hyperledger. So again, Hyperledger is a private and permissioned blockchain, or you can implement private or permission blockchain using Hyperledger, which is by IBM. Similarly, there are other blockchain platforms as well in the public permission domain as well as private permission domain. Now, coming back to the consensus algorithm, as we discussed earlier, in a blockchain, there is no single entity or no trusted entity that ensures a consistent shared view of the block of the ledger. This ledger is managed and maintained by a group of peers, and they need to agree on a shared consistent state of the ledger. So this agreement on the shared state of the ledger, this is manifested in different distributed systems problem, which have been derived or which are a transformation of the Byzantine generals problem. So that's a classical problem in computer science, Byzantine general problems. So that problem here is there are several divisions of Byzantine army which are camped outside an enemy city. Each division is guarded by or commanded by one general. So you have several divisions here, and all these, each division is commanded by a general. Now, all these generals, they need to reach an agreement on a common battle plan. So the agreement is on whether to attack or whether to withdraw or retreat. So all these generals, they are far apart and they cannot directly communicate with each other. They can only communicate by sending messages to one another. And each general assess the situation from his or her vantage point and send a message to the other generals whether to attack or withdraw. However, some of the generals may be traitors, and they will try to prevent loyal generals to reach an agreement. So, for example, if you see here in this figure, this general sends an attack message to all other generals. Similarly, this general sends withdraw message to all other generals. In that sense, these are honest generally. Either they may differ in the plan, but they are honest. They are not confusing other generals by sending mixed messages. But if you look at this general, that general has sent an attack message to these two generals, but sent a withdraw message to this general. So this this general is a malicious general because he wants to confuse and want to prevent all these loyal generals to reach an agreement. So if one general attack, another general retreat, the army would lost. So that will fail. So the idea here is to have an agreement among all the loyal generals on a common action plan, considering that there may be some traitors. But the assumption here is the traitor generals or the traitors are in minority. So that's the classical Byzantine general problem, which is manifested in different distributed systems applications where consensus is required among multiple peers, and all these peers cannot be trusted. This is the similar case in the context of blockchain, where you have multiple peers who each of these peers have their own view of the ledger or their own copy of the ledger, and all of them need to agree on a common state of the ledger. And some of these peers may be malicious or may not be honest. So there are three types of consensus protocol. There are many consensus protocols, but there are three main types of consensus protocols that are used in these distributed applications, or specifically in blockchain. The first one is proof of work. Second is proof of stake, and then third one is practical Byzantine fault tolerance problem. Practical Byzantine fault tolerance protocol. So in proof of work, each node or miner which is responsible or which is adding transactions to his or her copy of the blockchain, that miner solves a computationally intensive puzzle, and the miner who solves the puzzle first is considered as the one who is telling the truth, meaning all the transactions in the block generated by that miner are valid, and all the transactions in the miner blocks can be validated by other miners or other peers, because as we know earlier, as we discussed earlier, mining is a difficult problem. Once you have a solution of that puzzle, it's easy to verify. So everyone can validate whether the block generated by a miner includes all the correct and consistent transactions or not. So the result of computing the puzzle, the result of verifying the puzzle can be verified easily, and thus it helps others to validate the block generated by a miner. We are going to discuss that proof of work in more detail when we discuss the Bitcoin blockchain. Now, in proof of stake, basically each node who is involved in that consensus process or mining process, they put their stake by providing some security amount or by depositing a security amount, and whoever has the highest stake becomes the winner. Now, if that node is found to be cheating, that node will forfeit or lose its security deposit. So which one has a higher stake becomes a winner, but if that node is found to be cheating, that node will lose the security amount. Some blockchain also use this PBFT, Practical Byzantine Fault Tolerance protocol, where consensus is reached if more than 2/3 of the nodes in the blockchain are honest. So this is a critical assumption. If you have less than 2/3 of the nodes are honest, you cannot always reach a consensus. But if more than 2/3 nodes are honest, they will eventually reach a consensus. The proof of work is used in Bitcoin blockchain, and we are going to discuss that in the Bitcoin blockchain as well as in other public permissionless blockchains. The proof of stake and practical Byzantine fault tolerance algorithms, they are mostly used in permissioned or private blockchains. Now let's discuss this Bitcoin, which is one of the first applications that use the blockchain platform. This Bitcoin blockchain that was invented in 2008 by an unknown person or a group of unknown person who use the synonym Satoshi Nakamoto. This is not the name of an actual person. So that was a fake name or pseudonym. So nobody knows who that Satoshi Nakamoto is, whether it's a single person or it's a group of persons who invented that blockchain. Now, Bitcoin, if we come to Bitcoin, this is the largest cryptocurrency to date. The current number of Bitcoins that are in circulation are 18,665,750. I mean, that number, I looked at it a couple of hours ago. So this is today around 3 p.m. One important point is that the total number of Bitcoins that can ever be generated, they cannot exceed 21 million. So 21 million is the upper bound on the number of Bitcoins that can ever be in circulation. The current price of Bitcoin, again, that is a couple of hours ago, was $55,048.52. And if you multiply this price by the total number of Bitcoins that have been created, this amounts to 1.03 trillion US dollars. So I mean, this is huge amount, more than economies of several countries, even several developed countries. Now, but one critical aspect here is this Bitcoin blockchain. The throughput in terms of the number of transactions per second is quite low. So, for example, Bitcoin blockchain processes 7 transactions per second, whereas if you consider Visa credit card, their throughput is around 1700 transactions per second. So Bitcoin transaction rate is more than 250 times slower than Visa transaction rate. Now, when we consider Bitcoin, again, there are several security questions that come to our mind and we need to answer those. For example, am I paying the right person? If I'm receiving some amount, is he the right person? I'm not talking to an impersonator. Number 2 is related to integrity. If I'm receiving some Bitcoins, is it double spent? Since this is digital asset, anyone can generate multiple copies of that. So am I receiving the actual amount or whatever amount I am receiving from the other person, that amount is double spent. Double spent meaning that I use the same Bitcoin to pay 2 or more people. So that's an integrity question. Also, can an attacker, since we cannot trust everyone on the Bitcoin blockchain, there may be attackers or malicious nodes. Can they reverse or change the transactions? Finally, are my transactions private or anonymous? So let's see how these can be answered. So for the authentication question, that can be answered by following the public key infrastructure and using the digital signatures. So the digital signatures are unique to everyone and they can be verified. So every person who is transacting on the Bitcoin blockchain holds a public key, and all these transactions they record the public key of both payer and pay. So there cannot be any impersonation there. The PKI infrastructure and digital signatures take care of the impersonator problem. About the integrity, again, as I said, Bitcoin is a public blockchain, meaning all the transactions on the Bitcoin blockchain can be viewed by anyone. So if you want to check whether a transaction is not a fake transaction, it's not double spent, it's not reporting or including a double spent Bitcoin, anyone can check every transaction. So by looking at all the records associated with the public key of a pair, you can very easily verify that the pair has the required amount of Bitcoins in his or her account, and this is only the first payment of the Bitcoin. This transaction is the first payment of the Bitcoin which is included in that transaction. So you can verify very easily each transaction by looking at the entire record of that pair on the blockchain. Now, can an attacker reverse or change any transaction? Again, this is possible, but this requires more than 50% computation power of the entire network. So as long as no one can have more than 50% computation power of the entire network, these transactions cannot be reverted, modified, or changed. Finally, confidentiality, that is provided using pseudo anonymity, as I have discussed earlier. So let's discuss some of these questions in more detail here. So this is how a Bitcoin transaction looks like. As I said earlier, this is the pair information. So the key of the pair, public key of the pair, that is included here in the transaction. So anyone can verify that this is a valid public key. So again, in a PKI infrastructure, whoever issues the public key, they can verify who the pair is. This is the public key of the payee. This is the transaction amount. And this is the signature of the pair. To validate this transaction, we need to check the signature, and the signature can be very easily checked because we know the public key of the pair. We can go to the entity who issued that public key and check whether this signature corresponds to this public key or not. Similarly, we can check this amount is the first spending in this transaction. It's not double spend, by looking at the entire ledger or all the transactions made by this pair. So that answers that you are not talking to an impersonator, as well as the amount is not double spent. So each node or miner verifies that this is the first spending of the Bitcoin by the pair by looking at all the transactions by the person, by the pair. Okay, and we know the public key of the pair, as I discussed earlier. Now, you have all these transactions. These transactions have not been written in the Bitcoin blockchain yet. So we have miners who record all these different transactions and then generate a proof of work for all these transactions which are grouped in a block. Once a proof of work is found, then this block, which include record of all these transactions, is added to the main blockchain. I'm going to show you the entire process, but before I do, I want to comment on the complexity of this proof of work, or how proof of work is done. So proof of work is used to validate the transactions, to validate the unconfirmed transactions, whether these are correct or not, and they are not reporting any double spending of Bitcoins. So to compute proof of work, a miner first collects all the unconfirmed transactions that can fit in one block. The miner then computes the hash, the root hash of all these transactions. And then the miner basically includes the hash of the last block of the blockchain in this previous hash. And then the miner computes a nonce or a random value such that the hash value of previous hash, the transaction hash, and this nonce is less than a target value. Now, this target value is specified by the system, and this amounts to finding a hash value whose leading bits are 0. For example, the current target is a 32-bit hash value such that it has 19 leading zeros in it. So if you have a 32-bit hexadecimal hash values, the first 19 digits should be all zeros, and then you may have any other numbers. So 11 or 13 non-zero digits, but the leading 19 digits should be non-zero. And this work is exponential in the number of 0 bits required. This is not easy. So the way all these miners do is they get one number and then mine it and check whether its value is less than target or not. So they do that repeatedly, and there is a lot of work involved in this. So this is very computationally expensive. So the miner which solves this puzzle first is the one whose block will be added to the blockchain. So again, as I said earlier, computing this nonce value is very hard. However, given a nonce value, verifying whether the hash value of this previous hash, nonce, and transaction hash is less than target is very simple. You just need to apply the hash function and verify whether the output hash value is less than the target or not. Now, this slide explains how a block is added to the blockchain. As I said earlier, you may have transaction. Users may do transactions. So we can consider a simple transaction where A pays B $5. So this transaction will go into a pool of unconfirmed transactions. You will have a miner who will pick up some transactions from this pool that will fit in his or her block. So the miner will basically form a block by retrieving transactions from the pool, and then do the mining by computing this nonce value. As soon as the miner finds a nonce value, the miner is going to link its block to the last block of the blockchain and will broadcast this block to the entire network, which includes all other miners. So all other miners are going to validate this block by linking their block. So they are going to validate all the transactions in this block. If this is correct, then they will also prepare their own block, which will include different transactions, and they will link their block of transactions to the last block. So here in this particular example, we have validation by one miner, and this blockchain will grow. So the total number of blocks that will append it to this yellow block, basically each of these later blocks are validating this yellow block. So right now, all the transactions in this yellow block are validated by one block, but if this transaction is expanded to 2 blocks, all the transactions are expanded by 2 miners, and so on. Now it's quite possible that 2 or more miners may find a solution to their puzzle at the same time. So they will link their transaction to the latest block. For example, here block number 39 is computed by two different miners. Both of them link their block to the last block in the current blockchain. And the other miners, as I said earlier, will link their blocks to any of the two branches. So there is a fork. Miners will link their blocks to any of these two branches. So whichever branch of that fork becomes longer, later on all the miners will link to the longer branch and the shorter branch will be removed from the blockchain. So this is how a tie between two miners who come up with the solution at the same time is resolved. Now, as I said earlier, reverting or updating or modifying that blockchain is extremely difficult. And this slide shows you that. So for example, here there is a malicious peer who wants to modify this transaction. So in order to modify this transaction, the malicious peer has to compute the hash value of all the transactions and then modify this nonce value once this so that the output of the hash value is less than the target value. Now, once if the miner is doing that, while the miner is doing that, a new block is added to the blockchain, then the miner also needs to work on the next block and the next block and so on. So this is extremely difficult, and it's only possible if the miner has more than 50% of the computation power. If the miner doesn't have more than 50% of the computation power, this is virtually impossible. I've already discussed the privacy implications. Blockchain does not provide anonymity, it only provides pseudo anonymity. All the transactions remain on the blockchain. If it's a public blockchain, anyone can see the transactions on the blockchain, and through retroactive data mining or background information, they can find the real identity of the person making the transaction. Okay, now I'll spend the last few minutes on smart contracts. So in the blockchain, Bitcoin blockchain, when any miner validates a transaction, essentially the miner is running a script, and that script is written in a stack language. So that gave some idea to if you have a script which is a piece of code, why don't you write use that script, that functionality of the blockchain of executing the script to develop more interesting distributed applications. And that gave the idea of a smart contract, which is a program that runs on the blockchain and its execution is enforced by the consensus protocol, whether that protocol is the proof of work protocol, proof of stake protocol, or PBFT protocol. A smart contract essentially is an agreement. It's a self-executing agreement which is triggered based on some predefined conditions. So as you know, a contract is a legal document which includes clauses which needs to be evaluated. All these clauses are evaluated on the blockchain by executing the script. Now, if the condition corresponding to a clause is found to be true, then the code, appropriate code related to that condition is executed without any human intervention, and that basically is automatically triggered. I'll give you an example of a smart contract which is basically which is an example of a crop insurance, index-based insurance for crops. So let's consider there is a farmer and there is an investor. A farmer wants to buy a insurance for his or her crop, and you have an investor. So the way the farmer will do is both of them, the investor and the farmer, they will write a smart contract, and the farmer will deposit the premium amount to that smart contract. Similarly, the investor will deposit the payout amount to that smart contract. which is written and which will run on the blockchain. The condition of that smart contract is if the weather index, for example, if the rain falls, if the rain in that season, the rainfall in that season is less than the 30 years average, then the payout amount will be given to the farmer. Otherwise, the farmer will not receive any payout amount and the premium will be given to the investor. So once you have this smart contract at the end of the term period, the smart contract will call any weather service, and again you have weather service APIs that will check whether the rainfall level was 75% lower the 30-year historical average. If that is the case, the farmer will receive the payout amount. And again, all this amount will be in cryptocurrency, which is associated with the smart contract, and that is automatically settled, and that amount will be transferred in the farmer's account. If this condition wasn't true, if the rainfall was not lower than this 30-year historical average, it was average or higher amount, then the investor would have received the farmer premium. Now, there are several other examples or use cases where blockchain platform is used. For example, in the networks, it's used in DNS, in providing domain name services or developing domain name systems. Similarly, it's used in energy trading, also in tracking products in the food supply chain. In digital government or e-government, again, there are several use cases of these blockchain. You can read that. So I am I think I am running out of time. So I will end here. And if you have any questions, I'll be happy to receive any questions and try to answer those in whatever time I have left.
Thank you, Dr. Shafiq. I think that was a very, very insightful session. आपने मुझे मतलब जितनी मैं अभी ब्लॉकचेन के बारे में समझ सकी हूँ आपके उसके अंदर आपके सेशन के जरिए, इतनी समझ मेरी भी नहीं थी, तो बहुत शुक्रिया आपका. हमारे पास बिल्कुल सवाल हैं और मैं पूछ लेती हूँ. उसमें एक सवाल है जी, is the public key generated every time a transaction is initiated or public key is fixed for everyone?
Public key is fixed for everyone. However, I may generate multiple public keys. So it's like your bank account. आपका बैंक अकाउंट है, आपका एक भी हो सकता है, एक से ज्यादा भी हो सकते हैं, but you can make your transactions using your bank account. And you can write a check. Every time you write a check, you do not change your bank account. So public key stays with the person. It's the same unless someone creates a new public key, meaning that opening a new account.
Right. सही. और कुछ लोगों का मानना ये है कि बिटकॉइन एक बबल है. आपकी क्या राय है इस बारे में?
It's difficult to say. Again, हमने देखा है कि बिटकॉइन काफी अनस्टेबल रहा है. If you follow Bitcoin since I've been following it since 2016, and at one point it was less than 2,000 or close to $3,000. I think that was in 2018 or so. Then we have seen in the last year, most of the last year until October, it was varying between $10,000. Then all of a sudden, when Tesla invested there, similarly PayPal made their investment there, there is an exponential rise in its value. Now it will stay the same or not, it's difficult to say, but if Tesla, PayPal and all these big shots, they are investing in this Bitcoin, this means it will stay there unless there is a major withdrawal of investment from all these big shots. I would say it will maintain its value. But again, I'm not a financial expert, so you should not take my, I mean, this is just an opinion. You should take it with grain of salt.
Right. और sir, a question जो कि the golden question, do you own any bitcoins?
I do. I don't. In fact, if I were in the US, I would have, but I think now it's very difficult to make a wallet, especially given this rise in. So we are latecomers here, and we are academics here. So we usually follow what's happening rather than investing. So if I had that insight earlier, I would definitely have bought bitcoins.
सही है सर. मेरी तरफ से कुछ सवाल हैं. एक तो जिस तरह से आपने बेसिक समझाए, जहां से आपने बिटकॉइन की सिक्योरिटी के बारे में बात की, तो आपको सुनते हुए खास तौर पे जब आप बाइजेंटाइन जनरल्स प्रॉब्लम बता रहे थे, डोंट यू थिंक टेक्नोलॉजी इटसेल्फ एंड उसके पीछे जितनी भी सारी उसकी प्रोग्रामिंग है, it teaches you so much about human beings. अगर आप देखें तो आपकी इसके पीछे जो, जैसे आपने बोला कि आपका जनरल अगर मिक्स सिग्नल्स भेज रहा है तो उसके ऊपर फिर ट्रस्ट नहीं है, और अगर ट्रस्ट नहीं है so within that just loses its value. And the same happens in Bitcoin and in blockchain as well. So I think if anything you made me recall my यूनिवर्सिटी टाइम्स अगेन, एंड यू मेड मी अंडरस्टैंड कि हर चीज कितनी लिंक्ड है इंसान की फितरत से. उसी से आपके साइंटिस्ट ने भी ये सारी जो डिस्कवरीज और इन्वेंशंस की हैं, जो आपके कैरेक्टरिस्टिक्स हैं, वो अगर हम अपने अंदर ही ढूंढ लें तो शायद हम टेक्नोलॉजी को भी इतने अच्छे तरीके से समझ लें. सो आई थिंक बहुत इट वाज अ वेरी इंसाइटफुल सेशन. बहुत शुक्रिया आपका सर for being here today and for giving us your time, and our participants here and our attendees here surely learned a lot. There's one more question जो कि मेरे ख्याल से वक्त है तो मैं आपसे पूछ लेती हूँ. There's someone who's asking how to check if TX is in a Merkle tree if we only have a root. It's a very technical question.
No, you don't have a root. You can see all the transactions. So let me go to my first slide. This whole block is visible to everyone. So it's not like, so all the transactions, they are visible. Similarly, all the hash values are also visible. So now if I want to verify, let's say I want to verify this particular transaction. One way to verify that this particular transaction is part of this block or not is to compute the hash of all these different transactions and then combine them and see whether the root hash value is the same as the combination of all these transaction values. And then using the root hash, the previous hash and the nonce of that block, I check whether the resulting block hash value is less than the target value or not. So इसकी जो complexity है इस particular transaction को verify करने के लिए, I have to compute n hashes. Now, if I'm using a Merkle tree, what I can do is I have to compute the hash of this transaction, which is this, and then this hash value another. So I am following this path from the leaf node corresponding to the transaction to the root hash, which is log of n, and I'm using all the existing hash values. I'm not recomputing that. So Merkle tree reduce this complexity from computing n hashes to log n hashes. Does it answer your question?
Gee, I think it